Hello everyone, and welcome. Today I'm excited to take you through an insightful journey into how the Linux kernel works. My name is Kimmy AI, and we're kicking things off with this presentation titled, How the Linux Kernel Works. Over the next few slides, we'll explore the core concepts, inner workings, and key components that make the Linux kernel so powerful and versatile. So let's get started and dive into the fascinating world of Linux. Let's take a closer look at the contents of this section. We start with the network and protocol stack, which is fundamental for enabling communication between different systems and devices. This stack ensures data can travel reliably across networks, from physical transmission up to application-level protocols. Next, we have boot and initramps, the initial steps that occur when a system starts up. This phase is critical for preparing the environment, loading essential components so the system can operate smoothly. Moving on, the device and driver model forms the bridge between hardware devices and the software that controls them. It's what allows the operating system to interact seamlessly with various hardware components. Then, we reach process and memory core, which are at the heart of system operation. Processes are the active units executing tasks, while memory management ensures that each process has the resources it needs without interfering with others. And finally, we come to kernel foundations, the core principles that underpin everything else. The kernel manages hardware resources, enforces security, and coordinates all the components we've discussed. Understanding these layers helps us see how a complex system functions reliably and efficiently from startup to communication. Let's talk about observability and debugging, which are crucial for maintaining reliable and secure systems. Observability involves the ability to understand what's happening inside your system by collecting and analyzing data like logs, metrics, and traces. This helps us quickly identify issues and understand system behavior. Debugging, on the other hand, is the process of pinpointing and fixing problems once they've been detected. Together, these practices ensure we can maintain high availability and performance, even as systems grow more complex. Moving on to security and isolation, these are foundational principles to protect systems from threats and prevent unwanted interactions. Security involves implementing measures like encryption, access controls, and regular audits to safeguard data and resources. Isolation, meanwhile, ensures that different parts of the system or different tenants are separated so that a problem in one area doesn't cascade into others. Both are essential for building resilient, trustworthy systems that users can rely on. By integrating strong observability, debugging, security, and isolation practices, we create a robust environment that supports both operational efficiency and trustworthiness, which are key themes throughout our entire discussion. Let's take a closer look at kernel foundations. When we talk about kernels, we're really discussing the core part of an operating system that manages the hardware and provides essential services. It's like the brain behind the scenes, coordinating everything from memory management to process scheduling. The key point here is that the kernel acts as a bridge between the hardware and the software applications we use daily. It ensures that multiple programs can run smoothly without interfering with each other, maintaining system stability and security. Another important concept is that kernels can be designed in different ways, such as monolithic kernels, which include all services in one large block, or microkernels, which keep only the most essential functions in the kernel itself and run other services separately. Understanding these foundational ideas helps us see how operating systems are built and why they behave the way they do. This sets the stage for exploring how kernels influence overall system performance, security, and flexibility, tying directly into the broader themes of this presentation. Let's talk about what the Linux kernel actually is. At its core, it's a monolithic loadable module C program, and you'll typically find it stored in the /boot/vmlinux file. Now, what makes it special is that it's the only piece of code running in CPU ring 0. This gives it direct, raw access to everything: the instructions the CPU can execute, I/O ports for hardware communication, and physical memory pages. This high privilege level means the kernel has complete control over the system. It exposes two stable interfaces: the system call ABI, which is how user programs interact with the kernel, and the internal kernel module ABI, which drivers use to communicate with the kernel itself. Everything else, your shells, libraries, init systems like systemed, these all run in a lower privilege level in Ring 3. And technically, they are optional components. The kernel can function without them. So, understanding this helps us see how the kernel is the foundation. It's the core engine that manages everything, providing essential interfaces for safe and efficient operation of the entire system. Let's take a closer look at how processes are organized within the system. At the top, we have the user space, which is where applications and processes run. Here, the system maps the hardware into more understandable and manageable abstractions like processes, files, and sockets. Moving down, we come to the kernel, which acts as the bridge between the hardware and user space. It manages the core resources such as CPUs, RAM, buses, and devices, providing a foundation upon which everything else operates. Finally, at the base, we have the hardware itself. This three-level system model helps us understand how different parts of the computer work together. The kernel abstracts the hardware details, making it easier for user space to interact with the system efficiently and securely. This layered approach is central to the overall system design, ensuring that hardware complexities are hidden behind well-defined interfaces, which in turn simplifies application development and system management. So, the path that the system takes when handling a syscall is written in assembly language, and it's crucial that this process is atomic with respect to preemption. In other words, once we start this path, it must run uninterrupted until it reaches the handler, executes the syscall, and then reverses the path on exit. This ensures consistency and prevents race conditions or partial execution. When a syscall occurs, the system switches from user space to kernel space. This involves jumping to the handler, executing the syscall, and then reversing the process to return to user space. During this transition, the kernel must switch to its own stack, save the current registers, and raise the privilege level to kernel mode. On the kernel side, this transition is triggered by events like IRQs or page faults, or through instructions like int0x80 or sysenter. These instructions facilitate the switch from user mode to kernel mode, ensuring that the kernel has control to handle the request safely and efficiently. The overall goal here is to maintain a clear, controlled path for these transitions, ensuring that kernel entry and exit are smooth, secure, and predictable. This is fundamental to how operating systems manage system calls and interrupts, maintaining stability and security throughout the process. Let's take a closer look at the process and memory core. This part of the system is absolutely essential because it manages how data is processed and stored. The process core handles executing instructions, making sure that everything runs smoothly and efficiently. Meanwhile, the memory core is responsible for storing data temporarily or permanently, depending on the needs of the system. What's really important here is understanding how these two components work together seamlessly. The process core retrieves data from memory, processes it, and then sends the results back. This ongoing cycle is what enables the system to perform complex tasks quickly and accurately. Connecting this to the overall theme, think of the process and memory cores as the brain and memory of a computer, fundamental to its performance and reliability. Their efficient operation is key to achieving high-speed data handling and smooth user experiences. Let's take a closer look at the scheduling class, such as CFS, RT, and others. These classes determine how tasks are managed and prioritized by the scheduler. Moving on, we have the files, specifically the open file table, which keeps track of all files currently opened by a process. This is crucial for managing file access and ensuring consistency. Next is the memory descriptor, which points to the process's memory space, including its address space and associated resources. Understanding this helps us see how each process manages its memory. Then we have the state of the thread, which can be running, interruptible, or uninterruptible. This indicates whether the thread is actively executing, waiting for an event that can be interrupted, or waiting for a non-interruptible resource. Recognizing these states is key to understanding process behavior and scheduling. Every thread in the system is represented by a task struct, which is a core data structure. These are allocated using slab or slub allocators, which efficiently manage kernel memory. These task structs are linked together into a circular list, forming a ring that makes scheduling and traversing all threads straightforward. When we look at the task descriptor breakdown, it essentially provides a detailed view of what makes up each task struct. These components work together to enable the kernel to manage multitasking efficiently and ensure smooth process execution. Connecting all these points, we see how the kernel maintains an organized and flexible system for managing processes, their resources, and their states, which is fundamental to overall system performance and responsiveness. If the virtual memory area, or VMA, is absent, then attempting to access that memory will result in a segmentation fault, or SIGSEGV. This is a key safety feature to prevent invalid memory access. The same underlying path handles several important processes, including copy-on-write, swapping, and lazy allocation. These mechanisms help optimize memory usage by delaying allocation until it's actually needed. Actual page frames are allocated on demand, meaning physical memory is only used when necessary, which is efficient and scalable. When a page fault occurs, the system walks the VMA tree to determine where the fault happened. It then allocates the required pages and installs the appropriate page table entries, or PTEs, to map virtual addresses to physical memory. This dynamic management allows for flexible and efficient memory handling. The page fault handler is divided based on different regions of the user address space, such as the text segment, heap, mmap area, and stack. Each region has its own handling rules to ensure proper memory management. Overall, this structure enables a robust virtual memory system that supports multiple processes and complex memory operations seamlessly. This keeps fork cheap, only metadata is copied, while preserving POSIX semantics. Kernel threads skip this overhead by sharing the init. When a process calls do WP page, it allocates a new page, copies the content from the original, and then updates the child's page table entry to be writable and private. So instead of copying everything immediately, it sets up a copy-on-write mechanism. Now, when fork is called, it clones the task struct and duplicates the struct, but crucially, it marks all page table entries as read-only and shares the physical pages between parent and child. This sharing is efficient because it avoids copying all pages up front. The first time either process writes to one of these pages, the CPU raises a page fault, prompting the copy-on-write process. This way, actual copying happens only when necessary, optimizing memory usage and performance. This mechanism is fundamental to how Linux efficiently implements process creation and memory management. Let's take a closer look at how the Completely Fair Scheduler, or CFS, manages tasks across multiple CPUs. One of the key ideas here is load balancing. Essentially, tasks are moved between CPUs to keep their queues fair, preventing any single CPU from becoming overloaded while others are idle. This helps maintain a smooth and efficient system. Now, when it comes to selecting which task to run next, CFS always picks the most deserving task first. The most deserving task is determined by its virtual runtime, or runtime, which is a way of tracking how much CPU time a task has used relative to others. The task with the smallest runtime is considered the most deserving because it has had the least amount of CPU time so far. This selection process is organized using a data structure called a red-black tree. The leftmost node in this tree always represents the task with the lowest runtime, meaning it's the one that should run next. This structure allows CFS to quickly find and select the most deserving task, ensuring fairness and efficiency. Bringing it all together, CFS's internal design, using load balancing, runtime, and a red-black tree, works together to distribute CPU time fairly among tasks. This is fundamental to achieving the goal of a completely fair scheduling system that adapts dynamically to the system's workload. Let's take a closer look at the device and driver model. This model is fundamental because it helps us understand how hardware devices communicate with the operating system. Think of it as a layered approach where each device interacts with the OS through a specific driver. These drivers act as intermediaries, translating general commands into device-specific instructions. This separation of concerns makes the system more modular and easier to manage. By understanding this model, we see how the OS can support a wide range of hardware without needing to know the details of each device. The key points here are the role of the device itself, which is the physical hardware, and the driver, which acts as the translator and controller. This concept ties into the overall theme of system abstraction and modularity, making complex hardware interactions manageable and scalable. It's a critical foundation for how modern operating systems maintain stability and flexibility across diverse hardware environments. Let's start by looking at how drivers integrate with the device model. Drivers register a struct device driver, which includes a match table used to determine compatibility with various devices. This match table is essential because it helps the kernel know which driver should control which device, ensuring proper operation. Moving on, the Cobject core plays a crucial role in managing device objects. It handles reference counting, which keeps track of how many entities are using a device, preventing it from being destroyed prematurely. It also manages event generation, which is vital for notifying user space about device events, and it creates CISP symlinks that help organize device attributes in a user-friendly way. Each device node, represented by a struct device, carries specific attributes. These include hot plug attributes, which allow devices to be added or removed dynamically without rebooting. They also maintain driver binding state, indicating whether a device is bound to a driver or not. Additionally, these nodes have power management callbacks to handle power state transitions smoothly, ensuring energy efficiency and device stability. All devices are organized into a hierarchical structure, represented by a Cobject tree rooted at /sys/devices. This hierarchy provides a unified view of the device landscape, making it easier for both the kernel and user space to manage and interact with hardware components seamlessly. This unified device hierarchy is fundamental to ensuring consistent and efficient device management across the system, tying together driver registration, device organization, and power management into a cohesive model that supports dynamic hardware changes. Completion follows the reverse path. First, it starts with the IRQ, then moves through soft IRQ, and finally wakes up the user process. This sequence is crucial because it shows how the system handles I/O completion efficiently, ensuring that the user process gets the data it needs without unnecessary delays. Next, we see DMA to memory, which is a key part of high-speed data transfer. The host controller manages this process, directly transferring data between the device and memory, bypassing the CPU to improve performance. Then, we have the SCSI or NVMe command, which signals what operation needs to be performed on the device. These commands are sent through the device driver, which acts as the translator and controller for hardware communication. From there, the block I/O layer takes over, converting those commands into BIO or I/O requests. These are the fundamental units of I/O in Linux, representing specific read or write operations. When a read operation occurs, it might result in a page cache miss, meaning the data isn't in memory cache and must be fetched from disk. This triggers the block I/O stack to walk through its layers, initiating the data retrieval process. Overall, this slide illustrates the detailed journey of a read request, highlighting how each layer and component collaborates seamlessly to ensure data gets from disk to user space efficiently. This process is a perfect example of the complex, layered architecture that underpins high-performance I/O in modern systems. Let's take a closer look at how the interrupt handling flow works, starting with the hard IRQ. When a device triggers an interrupt, the hard IRQ acknowledges the device to let it know we've received the signal. At the same time, It masks further interrupts to prevent overload and schedules a worker to handle the more extensive processing later. Now, this is where the threaded IRQ worker comes in. It runs the actual driver code in process context, which means it can sleep and allocate memory, something the initial hard IRQ can't do. This separation allows for more flexible and safer handling of device requests without blocking critical system functions. Regarding priority, the threaded worker runs at priority 50 and is bound to the same CPU. This binding is crucial for cache efficiency because keeping the processing on the same CPU reduces cache misses and improves overall responsiveness. Finally, in modern drivers, we see a split in interrupt handling. This approach overcomes the traditional IRQ cannot sleep restriction, enabling low-latency responses while still allowing more complex, sleepable tasks to be processed safely in the threaded context. This flow ensures that interrupt handling is both swift and capable of handling more complex driver operations without compromising system performance. All right, let's walk through what happens from the moment the system begins to boot up, starting with the BIOS or UEFI firmware. These are the first pieces of code that run when you power on your machine. Their job is to load the boot sector, which contains the next stage of the boot process. Once the boot sector is loaded, grub2 takes over. It's a bootloader that extracts the kernel image, VM linas, and the initial RAM disk, or initted. Grub2 then decompresses the kernel, making it ready to run, and finally jumps to the kernel's entry point, which is the start function. Now, within the kernel itself, the first thing that happens is the relocation process. The kernel adjusts its memory addresses to fit into the system's memory map. It also builds important data structures like device tree and ACPI tables, which help the kernel understand the hardware it's running on. After these setup steps, the kernel calls start kernel. This is where the kernel initializes all its subsystems, like memory management, process scheduling, and device drivers, in a specific order to ensure everything is ready for the operating system to run smoothly. Finally, once the subsystems are initialized, the kernel spawns the initial process, known as the swapper or process 0, with PID 0. This process is essential because it acts as the parent for all other processes, effectively kicking off the user space environment. So, in essence, from BIOS or UEFI loading the boot sector, through grub2 extracting and loading the kernel, to the kernel setting itself up and starting the first process. That's the critical journey from system power on to kernel entry, setting the stage for the full operating system to come alive. Let's talk about boot and initramps. When a computer starts up, the boot process is the first step in getting the system running smoothly. The bootloader loads the kernel into memory, and this is where initramps comes into play. Initramps, or initial RAM file system, is a temporary root file system that the kernel loads into memory during the boot process. Its main purpose is to prepare the system environment, loading necessary drivers, mounting essential file systems, and setting up hardware, before handing control over to the main root file system. This step is crucial because it allows the kernel to initialize hardware that might not be directly supported by the kernel itself. Think of initramps as a staging area, helping the system get everything ready so the actual operating system can take over seamlessly. This process is vital for system flexibility and for supporting complex hardware configurations right from startup. Connecting this to our overall theme, understanding boot and initramps gives us insight into how Linux systems efficiently manage hardware initialization and ensure a smooth boot experience. All right, let's walk through what happens during the initial stages of the Linux boot process. The init script is responsible for loading all the necessary drivers, mounting the real root file system, and then executing switchroot to switch to that root. Now, the challenge here is that the kernel itself needs certain drivers to be able to read the root file system. But here's the catch. Those drivers are actually stored on the root file system itself. So, how does the kernel get those drivers in the first place? This is where the concept of the pivot comes in. We use a CPO archive, which contains all the essential drivers and tools needed for the boot process. This archive is loaded into RAM by the bootloader, so everything is available right from the start. The solution to this problem is what we call initramps. It's a small, initial file system that the kernel can access immediately after boot. It contains just enough drivers and tools to mount the real root file system. So, to sum up, the initramps is crucial because it provides the environment needed for the kernel to load the actual root file system, overcoming the chicken and egg problem of needing drivers to read the drivers themselves. This small, initial environment sets the stage for a smooth transition to the full system. Now, let's talk about how unknown parameters are handled during the boot process. These parameters are actually saved and exported through /proc/cmd line, which allows scripts to react accordingly. This means that any parameters not explicitly recognized by the kernel can still be accessed and used by scripts to adjust behavior or perform specific actions during startup. Moving on, we have what are called user space parameters. These are managed by early param macros, and what's important to understand is that they are processed even before kmalloc is ready. So, they're handled quite early in the boot sequence. These parameters are crucial because they control aspects like console verbosity, how much memory the system perceives it has, and even CPU mitigations. These are all things that need to be set up very early to ensure the system boots correctly and securely. Finally, let's look at what we call early parameters. These are typically specified on the kernel command line, like bootimage, root, quiet, splash, and so on. For example, the /proc/cmd line might look like this. Boot image equals /boot/vmlinas, root equals uuid equals, quiet splash. These parameters are parsed very early during boot, enabling the kernel to configure itself based on what's passed at startup. Understanding these command line options is key, because they influence how the kernel initializes and what options are enabled right from the start. Now let's look at how file descriptors are unified in the system. Essentially, sockets are now stored in the same FD table as regular files, which means that functions like select, poll, and epal can wait on mixed sets of file descriptors. This unification simplifies monitoring multiple I/O sources simultaneously. Next, I want to highlight the family-specific operations vector, such as TCP-prot and UDP-prot. These are attached to each socket, and they define the protocol-specific behaviors. When higher-level calls like send/msc are made, they dispatch through these ops, ensuring the correct protocol handling. Finally, when user code calls socket with parameters like yfinet and sockstream, the kernel responds by creating a struct socket and a struct sock in kernel memory. These structures form the backbone of the socket, encapsulating all the protocol and state information needed for communication. This layer of abstraction, connecting user calls to kernel data structures, is fundamental to how the socket layer and system calls work seamlessly together in networking. Let's take a closer look at the network and protocol stack. This is really the foundation that allows different devices and systems to communicate effectively. Essentially, it's a set of layered protocols that work together to transmit data reliably from one point to another. Each layer has its own specific functions, from physical transmission to application-specific processes. Think of it as a stack of building blocks, where each level depends on the one below it, but also provides services to the layer above. Understanding this stack helps us see how complex data exchanges happen seamlessly across networks. This concept is key to grasping how the internet and other communication systems operate smoothly behind the scenes. Now, once the RTT is sampled, it gets fed into the cubic congestion control algorithm, which helps manage the flow of data based on network conditions. As this process continues, the state transitions to established, meaning the connection is now active and the process wakes up to handle data transfer. Next, let's look at the steps for the TCP three-way handshake. First, we have the SYN message, which initiates the connection request from the client. Then, the server responds with a SYN-ACK, acknowledging the request and signaling readiness to establish the connection. This SYN-ACK is built in the connect process, which creates the SYN packet and queues it for output through the IP layer. Finally, the client sends an ACK back to confirm the connection, completing the handshake. During this entire process, the kernel handles socket lookup, sequence number validation, and the sending of the ACK, ensuring everything is synchronized and secure before data transfer begins. This handshake is fundamental because it sets the foundation for reliable communication between the client and server in TCP. Let's take a closer look at how connection tracking, or ConTrack, enhances packet filtering. It allows us to implement stateful rules, meaning we can recognize and handle packets based on their connection state, such as established or related. This makes our filtering much smarter and more dynamic. Now, when we build rule chains with tools like iptables or NF tables, these rules are translated into BPF-like bytecode. This bytecode runs efficiently within the kernel, enabling high-performance packet processing. Kernel modules come into play here as well. They register NF hookups, which determine at what point in the packet processing pipeline they operate, often based on priorities. This setup allows us to insert custom processing at specific stages. NetFilter provides 5 key hooks within the IP stack: PRERUTNG, local IN, forward, local out, and POSTRUTING. Each hook serves a distinct purpose, from inspecting packets before routing decisions are made to handling packets as they leave the system. Altogether, these components form a flexible and powerful framework for packet filtering and network security, seamlessly integrating connection awareness with efficient rule processing. Overload occurs when the dropped counter in /proc/net/softnet stat increases, indicating that the system is struggling to process incoming packets fast enough. To manage this, techniques like RPS and XPS spread RX and TX workloads across multiple CPUs, helping to balance the load and improve efficiency. When scaling, the driver typically disables IRQs, polls a certain number of packets, and then re-enables IRQs, which is a basic form of managing high network traffic. Recently, we've seen the introduction of NAPI polling, which is a more advanced approach. Instead of handling each packet with an IRQ, NAPI disables IRQs temporarily and polls a batch of packets, re-enabling IRQs afterward. This reduces the high CPU overhead associated with handling each packet individually, something that was quite inefficient with the old IRQ per packet method. In the context of high-speed networking, NAPI plays a crucial role by helping to mitigate the CPU load and improve overall throughput. It's a key evolution in how we handle network traffic more efficiently at scale, especially as network speeds continue to increase. Now let's talk about how access is managed via system calls. In this model, we have 2 main privilege levels: Ring 3, which is the user mode, and Ring 0, the kernel mode. The user mode, Ring 3, has full access to hardware resources, but it's limited in what it can do directly to ensure system stability and security. The kernel, operating at Ring 0, has unrestricted access to hardware and system resources. To enhance security, modern features like SMEP and SMAP add extra bits to prevent user mode pages from executing or being accessed while in kernel mode. This helps mitigate privilege escalation exploits, making it harder for malicious code to break out of its intended boundaries. System calls, which are the gateway for user programs to request kernel services, switch modes via the SYSCALL instruction. This instruction loads a fixed model-specific register, or MSR, into the instruction pointer, RIP, to transition into kernel mode. When the kernel is done, it returns to user mode using SYSRET. It's also interesting to note the historical context. x86 architectures support 4 privilege rings, but Linux primarily uses just 2, Ring 0 for the kernel and Ring 3 for user applications. The CPU enforces these privilege levels using mechanisms like page table US bits and segment descriptors to control access rights. This split between user and kernel privilege is fundamental to operating system security. It ensures that user applications are isolated from the core system, preventing accidental or malicious interference. This structure underpins the overall security and stability of modern computing systems. Now let's talk about security and isolation. These are critical concepts in ensuring that our systems remain safe and functional. Security, of course, involves protecting our data and resources from unauthorized access and potential threats. It's about implementing the right measures, like encryption, authentication, and access controls, to keep everything secure. Isolation, on the other hand, focuses on separating different processes or workloads so that if one fails or is compromised, it doesn't affect the others. Think of it like having separate rooms in a house. If there's a fire in one room, the others remain safe. Both security and isolation are key to creating a resilient system. They work together to minimize risks and contain issues, helping us maintain integrity and trust in our infrastructure. This ties into the overall theme of building robust, reliable, and secure systems that can adapt to various challenges. Namespaces provide isolation, meaning they allow different containers or processes to have their own separate view of the system resources. On the other hand, C groups or control groups help us set resource limits, making sure that each container uses only what it's supposed to. When you combine these two, they form the foundation of container technologies like Docker. For example, C groups are used to limit resources, such as CPU and memory, while namespaces isolate various system aspects. We see C groups at work with commands like clone, specifically clone with the clone_any_wpid flag, which creates a new process namespace. This is part of the container runtime that manages the lifecycle of containers. Each type of namespace isolates different global resources, like UTS, IPC, user, and C group namespaces, which handle hostname, inter-process communication, user identities, and group information. Then there are other namespace types like PID, mount, and network, which isolate process IDs, file system mounts, and network interfaces respectively. When we talk about namespaces and containers together, it's about creating a lightweight, isolated environment that mimics a full system, but within a shared kernel. This synergy of namespaces and C groups is what makes containers so powerful. They provide both isolation and resource management in a way that's efficient and flexible, perfectly aligned with the overall goal of containerization to run multiple, isolated applications on the same host without interference. Let's take a look at the modes in SE Linux. There are two main modes, enforcing and permissive. In enforcing mode, SE Linux actively denies actions that are not explicitly allowed and logs these denials. In permissive mode, it only logs the actions but still allows them to proceed. This distinction is crucial for understanding how SE Linux controls access. Now, the policy rules are written in what's called a type enforcement language. These rules specify exactly which transitions are permitted, and only if they are explicitly granted. This means there's a precise control mechanism in place, ensuring that only authorized interactions occur. An important component here is the security server, which checks these policies constantly. It consults what's called the Access Vector Cache, or AVC, millions of times per second. This rapid consultation allows SE Linux to efficiently enforce policies without slowing down system performance. Finally, SE Linux attaches labels to every object it manages, be it in nodes, sockets, or processes. For example, you might see labels like systemu, objectar, httpd log t, s0. These labels are vital because they tell SE Linux what type of object it is dealing with and what permissions apply, helping maintain a secure and organized environment. All of these elements, modes, policies, the AVC, and object labels, work together to enforce mandatory access controls, which are a core part of SE Linux's security model. Let's look at how we can use filtering with echo *TCP*, and set ftrace filter to zero in on specific code paths. This helps us reveal latency issues more clearly. By doing this, we can focus on particular functions or operations related to TCP, making troubleshooting more precise. Next, when we run echo function graph current tracer, we're effectively recording entry and exit points of functions with nanosecond precision. This creates a detailed call graph without needing to recompile the kernel, which is a huge advantage for dynamic analysis. ftrace stores data in per CPU ring buffers, meaning each CPU has its own buffer to record kernel functions during runtime. This setup allows us to instrument any kernel function on the fly, providing a flexible, real-time view of what's happening inside the kernel. Overall, ftrace and the function graph tracer are powerful tools for understanding kernel behavior, pinpointing latency, and optimizing system performance. They fit perfectly into our broader goal of gaining deep insights into kernel operations without disrupting the running system. Let's talk about observability and debugging, which are crucial for maintaining healthy systems. Observability is all about having the right tools and metrics in place so we can understand what's happening inside our applications in real time. It helps us catch issues early and understand their root causes more effectively. Debugging, on the other hand, is about diving into those issues when they do occur to identify and fix problems quickly. Together, these practices allow us to improve reliability and performance. They tie directly into the overall goal of building resilient, scalable systems that can adapt and recover efficiently. Keeping a close eye on system behavior and being able to troubleshoot swiftly are key to delivering a seamless experience for users. Let's walk through the process of eBPF and programmable tracing. First, you start by writing a C program specifically for tracing. This is where you define what events or data you want to monitor. Next, you compile this C code into eBPF bytecode using LLVM. The bytecode is then checked by the kernel verifier to ensure safety and security, making sure it won't harm the system. After verification, the bytecode is attached to K-probes, which are kernel probes that allow us to hook into specific kernel functions. Once attached, the data streams from these probes directly to user space, so we can analyze or visualize it in real time. For example, tools like tcplife can trace TCP sessions, and BioSnoop can log disk I/O activities. This entire process showcases how flexible and powerful eBPF is for creating custom, safe, and efficient tracing solutions within the kernel. Let's take a moment to look at some common commands that are essential during crash analysis. For example, BT, which stands for backtrace, helps us trace the sequence of function calls leading up to the crash. Then there's KMS, which shows us the slab caches, giving insight into memory allocations. And with files PID, we can examine the open files associated with a specific process. The crash utility itself is quite powerful. It imports the VM Linux symbol file, which provides symbol information needed for analysis. It walks through task lists, memory zones, and stacks to piece together what was happening at the time of the crash. Now, when the kernel encounters a panic, the system uses kexec to load a crash kernel into reserved memory. This new kernel then captures the contents of /proc/vmacore, which is an ELF image containing a snapshot of the previous memory state. Understanding how crash and vmacore analysis works is crucial for diagnosing issues effectively. It allows us to reconstruct what went wrong, analyze memory dumps, and ultimately improve system stability and reliability. Now, the tracing tools we've discussed enable us to inspect any layer of the Linux kernel without disrupting its operation. This means we can look inside the kernel as if it were an open book, rather than a sealed black box. Remember, the Linux kernel itself is essentially a big C program that takes all sorts of hardware, processors, memory, I/O devices, and makes them work together as a unified POSIX system. It does this through a series of well-defined layers, each with specific entry points for interaction. Understanding these layers and where they intersect is crucial. It allows us, as engineers, to fine-tune performance, troubleshoot crashes more effectively, develop new drivers, and even build containers. So, by putting all these tools and concepts together, we gain a comprehensive view of the kernel's inner workings. This holistic understanding is key to optimizing and customizing Linux for a wide range of applications. So, as we conclude today's presentation, I want to highlight that this milestone date, January 1st, 2025, marks a significant moment in our journey with Kimi AI. It's not just a date, it symbolizes the future we've been working towards. Kimi AI represents our commitment to innovation and enhancing how we interact with technology. Thank you all for your attention and engagement throughout this journey. Your support and collaboration are what drive us forward. Remember, this isn't just the end, it's the beginning of exciting new opportunities with Kimi AI leading the way. Once again, thank you, and I look forward to what we will achieve together in the future.